What happens to cancer cells when you don't eat for a whole day? Sounds like a strange question, but science has discovered something remarkable about what goes on inside your body when food stops coming in. Your healthy cells adapt, your immune system sharpens, and cancer cells, they start to struggle. Right now inside your body, there's a constant battle happening. Your immune system is identifying and destroying abnormal cells before they can become dangerous. Most of the time, you never even notice. But what if you could tip the scales in your favor? What if something as simple as not eating for 24 hours could give your body an advantage in this fight? Today, we're going inside the 24-hour fast to see exactly what happens hour by hour to the cells that could one day threaten your life. And what you learn might change how you think about the simplest thing you do every day: eating. But before we dive in, this is educational content, not medical advice. If you're considering fasting, talk to your doctor first, especially if you have any health conditions. Now, to understand why fasting affects cancer cells differently than normal cells, we need to go back almost 100 years to a German scientist named Otto Warburg, and a discovery that would eventually change how we understand cancer itself. This discovery sat largely ignored for decades, but in recent years, it has become the foundation of modern cancer metabolism research. And once you understand it, everything about fasting and cancer will make perfect sense. In 1924, Warburg was observing cancer cells in his laboratory, and he noticed something strange. These cells were consuming glucose in a completely different way than normal cells. At the time, scientists believed cancer cells were simply normal cells that had lost control of their growth. But Warburg saw something deeper, something fundamentally different about how these cells generated energy. Here's what happens in a healthy cell. When glucose enters, it goes through a process called the TCA cycle, also known as the Krebs cycle. This process uses oxygen to completely burn glucose, extracting maximum energy. From a single glucose molecule, a healthy cell produces 32 to 34 units of energy, called ATP. It's efficient. It's thorough. It extracts nearly everything useful from that glucose molecule. But cancer cells, they do something bizarre. They convert glucose directly into lactate even when there's plenty of oxygen available. This process only produces 2 ATP per glucose molecule. That's 15 times less efficient than what healthy cells do. For decades, scientists were puzzled. Why would cancer cells choose such a wasteful path? It seemed to make no evolutionary sense. If cancer cells are competing for resources, why would they use resources so inefficiently? The answer, it turns out, is speed. The flow of glucose to lactate is nearly 100 times faster than going through the full TCA cycle. Cancer doesn't care about efficiency. Cancer cares about growing fast. It needs to divide rapidly, spread quickly, and outcompete the body's defenses. And to maintain this rapid growth, cancer cells need one thing above all else: a constant supply of glucose. Non-stop, without pause, without interruption. This creates a dependency, an addiction really. Cancer cells become so reliant on this fast glucose pathway that they lose the ability to use other fuel sources. They've traded flexibility for speed, and that trade-off comes with a fatal weakness. Think of it this way. Cancer cells are like a high-performance sports car that only runs on premium gasoline. Fast, powerful, but with only one fuel option. Your healthy cells are like hybrid vehicles. They can run on gasoline, electricity, or even diesel. When the gas station closes, the hybrid switches to electric mode and keeps moving. But the sports car, it stops. The engine dies. This isn't just theory. This principle is used in medicine every single day. PET scans, one of the most common tools for detecting cancer, work exactly on this principle. Doctors inject radioactive glucose into your body. Cancer cells hungry for glucose gobble it up faster than anything else, and they light up on the scan. The Warburg effect isn't just a laboratory observation, it's a diagnostic tool. And here's why this matters for fasting. Cancer cells cannot switch to alternative fuel sources the way healthy cells can. When you fast, glucose levels drop and ketones rise. Your healthy cells adapt, switching smoothly to ketone metabolism. But cancer cells are trapped. They're still waiting for glucose that isn't coming. This is their Achilles heel. And when you understand this, everything about fasting and cancer starts to make sense. So let's walk through what actually happens inside your body during a 24-hour fast, hour by hour, starting from your last meal. During the first 4 hours after eating, your body is in what scientists call the fed state. Insulin spikes to help shuttle glucose into your cells. Blood sugar is high. And IGF-1, insulin-like growth factor, a hormone that promotes cell growth, is also elevated. This is important to understand. IGF-1 doesn't just promote growth of healthy cells. It promotes growth of all cells, including precancerous ones. Higher IGF-1 levels have been associated with increased cancer risk in multiple studies. When you eat, especially when you eat frequently, you keep IGF-1 elevated. Your body is in building and storage mode. Every cell is being nourished, including cells that perhaps shouldn't be nourished. This is the environment cancer cells love. Glucose is abundant. Growth signals are strong. If there are any precancerous cells lurking in your body, they're being well fed right now. The sports car has a full tank. You feel satisfied, maybe a little sleepy after a big meal. Energy stable. Nothing unusual from your perspective. But here's the thing. If you eat continuously every few hours putting food in, you keep your body permanently in this state. Growth signals never turn off. Cancer cells never run low on fuel. Some researchers believe this constant fed state, this never-ending supply of glucose and growth signals, may be one reason cancer rates have increased in modern societies where food is always available. What happens when you stop eating? Between hours 4 and 12, things begin to shift. Insulin starts dropping. Your liver begins releasing glycogen, its stored form of glucose, to keep blood sugar stable. IGF-1 also starts declining. Your body is transitioning from building mode to maintenance mode. This is the transition phase. Nothing dramatic yet, but the foundation is being laid. At a molecular level, sensors inside your cells are detecting the change in nutrient availability. A protein called AMPK, often called the master metabolic regulator, begins activating. AMPK is like an alarm system that detects low energy states and starts making adjustments. It tells cells to stop growing and start conserving. But cancer cells, with their mutated signaling pathways, often can't respond properly to these signals. Cancer cells begin to sense the change. Glucose is still available, but not as abundant as before. The sports car glances at its fuel gauge. The needle is starting to move toward empty. Not an emergency yet, but there are signs. You might start feeling mild hunger at this stage, especially if you're used to snacking frequently. Some people feel irritable or have trouble concentrating. This is normal. Your body is adjusting. These feelings typically pass. And this is just the beginning. Most people stop here. They feel hungry and eat. But if you continue past hour 12, something interesting starts to happen. Between hours 12 and 17, this is where everything begins to change. This is the inflection point. Liver glycogen is running out. Your liver starts producing ketones, an alternative fuel source made from fat. Insulin is now low. IGF-1 has dropped significantly. And a process called autophagy begins ramping up. Autophagy, from the Greek words meaning self-eating. This is when your cells start cleaning up and recycling old damaged components. In 2016, Japanese scientist Yoshinori Osumi was awarded the Nobel Prize in Medicine for discovering the mechanisms of autophagy. He found that this isn't just cellular housekeeping, it's a sophisticated defense system. Working with baker's yeast in the early 1990s, Osumi identified 15 essential genes that control this recycling process. He showed that when cells are starved of nutrients, these genes activate a remarkable cleanup operation. His breakthrough revealed that autophagy can identify and eliminate damaged proteins malfunctioning mitochondria and, most importantly, precancerous components. Think about what this means. Your cells have a built-in quality control system that specifically targets damaged dysfunctional parts. Parts that, if left alone, could eventually become cancerous. And this system activates when you stop eating. Your cells literally start eating the parts of themselves that could become dangerous. It's like having a Marie Kondo inside every cell, identifying what sparks joy and recycling what doesn't. Except instead of cluttered closets, it's identifying misfolded proteins and damaged DNA that could lead to cancer. Meanwhile, your healthy cells are beginning to switch to ketone fuel. They're adapting seamlessly. But cancer cells, because of the Warburg effect, cannot make this switch. They're still waiting for glucose. Their metabolic machinery is locked into glucose-only mode. The sports car is now running low on fuel and there's no gas station in sight. Some people feel stronger hunger at this stage, but many report the opposite. Hunger starts fading, replaced by clearer focus. If you experience severe dizziness or rapid heartbeat, stop and eat something light. Listen to your body. Now we enter the final stretch. Hours 17 to 24. This is where the real transformation happens. Autophagy is now in full swing. Your cells are actively cleaning and recycling. IGF-1 can drop by up to 70% during extended fasts. Research from Professor Valter Longo's lab at USC showed that a 72-hour fast reduced IGF-1 by 70% and increased its inhibitor, IGF-BP1, by 11-fold. Even at 24 hours, significant changes are happening, and a phenomenon called differential stress resistance reaches its peak. This is the breakthrough discovery of Professor Valter Longo at the University of Southern California. When you fast, healthy cells enter a protected state. They reduce activity, increase defenses, and essentially hunker down to wait out the shortage. They activate ancient survival pathways that have been conserved through millions of years of evolution. But cancer cells cannot do this. Here's why. Cancer cells have mutations in genes like RAS-AKT and mTOR. These are growth signaling pathways that are permanently stuck in the on position. It's like having a gas pedal that's jammed to the floor. They can't slow down. They can't switch to conservation mode. Their own mutations, the same mutations that allow them to grow uncontrollably, prevent them from adapting to nutrient scarcity. Professor Longo describes it like the difference between bears and hummingbirds. Bears can hibernate when food is scarce. They slow their metabolism, conserve energy, and wait for better times. Hummingbirds cannot. They need to eat constantly or they die. Their high-speed metabolism has no off switch. Cancer cells are like hummingbirds. They have no pause button. They cannot slow down. They cannot enter protection mode. And in a fasted state, this becomes their downfall. The sports car has now run completely out of fuel. The engine is dead. Meanwhile, your hybrid, your healthy cells is running smoothly on electric power, on ketones. Cancer cells are trapped, exposed, and vulnerable. And your newly activated autophagy system is actively seeking out damaged cells to eliminate. Many people report a feeling of mental clarity at this stage, sharp focus, stable mood. Some describe it as a sense of calm alertness they've never experienced before. This is ketones feeding your brain. Your body has fully adapted. You're no longer hungry. You're in a metabolic state that your ancestors experienced regularly between successful hunts. A state your body was designed for. But there's another piece to this puzzle: your immune system. In 2024, researchers at Memorial Sloan Kettering Cancer Center discovered something remarkable. They had mice fast for 24 hours twice a week, and they tracked what happened to NK cells, natural killer cells. These are your immune system's special forces specialized in destroying cancer cells and virus-infected cells without needing prior exposure to them. Unlike T cells, which need to be trained to recognize specific threats, NK cells can identify and attack abnormal cells immediately. They're your first line of defense. And what the researchers found was surprising. During fasting, NK cells migrated to the bone marrow, where they were exposed to high levels of a signaling protein called interleukin-12. This trained them to produce more interferon gamma, a cytokine crucial for killing tumors. The NK cells were essentially being reprogrammed to become more effective cancer killers. At the same time, other NK cells learned to use fatty acids as fuel instead of glucose. They underwent what the researchers called metabolic reprogramming. Why does this matter? The environment around tumors is hostile to immune cells. Tumors are greedy. They consume all the glucose in their vicinity, creating a landscape rich in lipids but starved of the fuel most immune cells need. Normal NK cells would die in this environment. They'd enter the tumor, run out of energy, and fail. But NK cells trained through fasting can survive and fight. They've learned to burn fat for fuel, the very fuel that's abundant in tumor environments. It's like sending your immune system's soldiers to boot camp, teaching them to survive in exactly the harsh conditions where they need to operate. The researchers noted that blood tests in humans showed similar redistribution of NK cells during fasting, suggesting this mechanism may also apply to people. Now, something important I need to say. If you or someone you love is currently fighting cancer, or if your body is weakened for any reason, please listen carefully to this part. While the science shows promise, cancer patients often already suffer from malnutrition. The disease itself and the treatments used to fight it can drain the body's resources. Your body needs protein and energy to maintain muscle, support your immune system, and recover from treatment. Chemotherapy and radiation demand that your body has enough strength to repair itself. Fasting done incorrectly can worsen a condition called cachexia, the severe muscle wasting that affects many cancer patients. This is a serious concern. Losing muscle mass can weaken your immune system further and reduce your ability to tolerate treatment. Some medications need to be taken with food. And the way your body processes drugs can be affected by fasting. Timing matters when it comes to cancer treatment, and adding fasting without guidance could interfere with your protocol. It's also important to understand that while the research is exciting, large-scale clinical trials in humans are still ongoing. Professor Longo's work is promising, but we're still learning exactly how, when, and for whom fasting may be beneficial as part of cancer treatment. If you're undergoing cancer treatment, always talk to your oncologist before trying any fasting regimen. Ask about the fasting mimicking diet. The protocol. Professor Longo developed specifically as a safer alternative that provides some nutrients while still triggering many of the beneficial fasting responses. Some hospitals are conducting clinical trials. You might ask your doctor about opportunities to participate in supervised research. The goal is to support treatment, not replace it. And if your body is weak right now, prioritize recovery first. High quality nutrition might be more important than restricting food at this stage. Work with your medical team to find the right approach for your specific situation. So, after all this science, what's the real takeaway? Perhaps it's realizing that your body is smarter than you thought. It evolved over millions of years with sophisticated protection mechanisms. Fasting isn't starving your body. It's activating survival programs that have been encoded in your DNA since the dawn of humanity. Your healthy cells know how to adapt. Your immune system can be trained, and cancer cells have a fatal weakness, an addiction to glucose that becomes their downfall when fuel runs short. Now, I want to hear from you. Some doctors say never fast beyond 16 hours. Others point to research showing benefits at 24, 48, even 72 hours. Where do you draw the line? I'm genuinely curious what you think. Drop your opinion in the comments. And if you've ever tried fasting longer than 16 hours, how did you feel at hour 17? That's the inflection point where autophagy really kicks in. Share your experience below. If this video changed how you think about eating and health, share it with someone you care about, especially if they're concerned about cancer prevention. Subscribe so you don't miss what's coming next. In the next video, we're diving into another question. What happens if you break your fast the wrong way? The mistake almost nobody talks about. Thanks for watching. I'll see you in the next one.